Take this example. We have f of t is e to the power of minus a t u t. Now, we would like to calculate the energy content in the signal, energy available from the signal in two ways. Time domain. Do it in the time domain, energy available from integral from minus infinity to infinity of f square t dt, that is minus infinity to plus infinity of e to the power of minus 2 a t dt, but this lower limit is not correct because f square t exists only from t equals 0 to infinity. Therefore, you have to write substitute here from 0 to infinity e to the power of minus 2 a t dt. Therefore, this will become e to the power of minus 2 a t divided by minus 2 a evaluated between 0 and infinity. At the upper limit, this is going to be 0 because we are taking to be a positive quantity, and at the lower limit, of course, this is 1, this will become 1 over 2 a. So, 1 over 2 a joules is the total energy available from the signal. Let us work this out in frequency domain. F of j omega is 1 over j omega plus a, but we were talking in terms of energy. Therefore, energy density is f of j omega magnitude squared is 1 over omega squared plus a squared, so many joules per cycle per second. So, the total energy available from the signal is the 1 over 2 pi times the integral from minus infinity to plus infinity of 1 over omega squared a squared du. And this can be shown by substituting omega, put omega as a tan theta and carry out this integration, and you can show that this is indeed equal to 1 over 2 a. Which is exactly the result that we have obtained earlier. If you plot f of j omega squared versus omega, the energy density is a function of frequency omega, you will get a curve like this. So, this is the energy density. So, this gives us an idea of where the energy is concentrated, at what frequency bands there is more energy. Now, as you can see, there is a lot of energy in the low frequency band centered around the DC. At higher frequencies, the energy is somewhat less. This additional information is obtained through the Fourier transform analysis as compared with the time domain analysis. Let us see how such a concept can be made use of in practice. Let us assume that this particular f of t, which we had, this exponential signal, is put through a low pass filter and we get an output signal f naught of t. This low pass filter has a characteristic like this: h of j omega magnitude A low pass filter essentially allows all frequencies up to a certain point and then shuts off all other frequency components. So, let us imagine that our low pass filter here has a cutoff frequency equal to A and minus A. In other words, in the spectrum that is available for the given f of t, all frequency components having a magnitude omega greater than A become 0. That means, h of j omega we are talking about the transfer function or the system function relating f naught of t and f naught of t is equal to 1 for omega less than or equal to A and 0 otherwise. So, essentially what we are doing is this low pass filter is such that it cuts off all frequency components beyond a certain value A. So, if this is A and this is minus A, as far the output is concerned, f naught of t, the corresponding energy density f naught of j omega squared would be the one which contains frequency components within this band only. That means, it will have only this minus A to plus A, the rest of the terms being cut off. And so, suppose I want to know what is the energy available from f naught of t, then you have to take the same function, but integrate between minus A to plus A rather than from minus infinity to plus infinity. So, we have the energy available from f naught of t equals the integral of 1 over omega squared plus A squared, that is the energy density, into times d omega over 2 pi. The integral now is from minus A to plus A instead of from minus infinity to plus infinity, and then by making use of standard substitution that omega equals A tan theta, this can be shown to be 1 over 4 A joules. It means that out of the total energy available from the input signal f t, which is 1 over 2 A joules, 1/2 of that energy resides in the band frequency band omega from minus A to plus A. So, since when signals are transmitted through linear systems like a low pass filter, and these systems are characterized quite nicely in terms of the system function h of j omega, and if you would like to find out the properties of the signals that come out of the system or the response of the system, then frequency analysis in this manner turns out to be a very convenient tool, because these filters like this are characterized in terms of their frequency response, not in terms of their time response, and therefore, the energy available from the f naught t can be more conveniently handled in terms of frequency characteristics of the signal, in terms of the spectrum as shown here. If we wanted to do the same analysis in terms of time domain, then it would be much more difficult, because you have to characterize the filter in terms of its time response, which can be done, but it is much more complicated. So, this example illustrates how we can utilize the energy concepts also in finding out the characteristics of various signals. Okay.